Welcome back. So now we are going into the other side 2 of the lecture with a look back at SQL, a brush up. So something you've already seen in information systems for engineers. However, I both want to give you a warning and also to make you not worry. What's going to happen today is that half of you will be bored because they already know that, and half of you might be a bit impressed because I'm throwing at you a lot in 1 hour. You don't have to worry about that. First, the main goal here is just to learn SQL. Next week, you're going to have exercises to learn SQL. So you're going to be able to practice. And again, practicing is the way you learn SQL. SQL is easy to learn. It was meant to be easy to learn. So this is why you shouldn't panic, right? All right, just saying that. So if you feel it's a lot, don't be discouraged. This is not a normal lecture. The pace throughout the semester is slower. It's just here the points to fast track you through the main ideas of relational databases, right? And I have a question for you, also, so that you see that in the case that you didn't know SQL before, so that you don't feel alone, I want to show you that poll that we are doing right now. So how familiar are you with relational databases? What is this? I know the basics. I attended a bachelor's level database course, maybe information systems for engineers, or you even write video games with data in the 6 normal form. By the way, it's not a joke. There was research, I think it was at Cornell University. There was a professor, I think, Johannes Kerker, who was researching how to see these real-time strategy games as a database problem. Basically, you keep updating the database and you have the state of the world. Gave a talk at ETH a while ago. Okay, so you see, there are quite a lot of you who never heard of SQL. So you see, you're not alone. If that's the case. Some of you might know the basics, but need to brush up. So that's good. We're going to do this today. If you already know SQL and attended courses, just sit back and enjoy the ride. You're just going to bring it back to the top of your mind. And we have one power user of the 6 normal form in the class. Fantastic. All right, and by the way, you can interact on the forum, on the chat. So if you don't know SQL, then you can ask on the chat. If people who know SQL can also help and answer questions. I don't know, I haven't tested if Ethel can actually write SQL. What I know for sure is that ChatGPT can produce SQL. I tried to put in ChatGPT the schema of an exam question. So the schema with the columns attributes. I pasted the exam question in English, and ChatGPT outputs not only the SQL query, but explanations about the details of how the SQL query was produced. So just a hint that if you want to learn SQL, then maybe ChatGPT can help too. Again, with a word of warning, it can hallucinate, it can make mistakes, but maybe that's a good way of enhancing your learning. All right? But of course, the best is to interact among each other, right? There's no better way to learn than to teach. So if those of you who feel comfortable enough can explain to others, that's a great way to master the material even more. All right. I'm going to switch back to the slides. All right. By the way, I encourage you to try it. I mean, send us screenshots. Try to take the exam questions of the past few years, put the schema in the question, and see what ChatGPT does. Share the screenshots. It would be fun to look at this. All right. So now, let me go through this very special and unusual lecture, because again, I'm going to throw at you all the relational and SQL part. Going to be careful, though, to do it with a reasonable speed. This here is Edgar code. He's considered to be the father of modern databases. He's the one who had this brilliant idea called data independence, which is the idea that the only thing the users should ever see is something extremely simple, tables, the ones that you saw in clay tablets thousands of years ago. Everybody understands the table. In fact, there has been social science studies that ask people like, what do you understand best? So they gave them tables, they gave them pie charts, like all the things you find in infographics, right, in newspapers. The one thing people understand the best is tables, right? So this is why users should see tables. All the rest is hidden. The physical storage here should be a hidden detail. In fact, it's so hidden that you can swap it. This, I said, is also a relational database. It might be a bit slower because whenever you have an update, you need a scribe who actually modifies the clay tablet. It might be very slow, but it is still a relational database. You might have, in some way, some spreadsheet software, probably not the best way to deal with a relational database, but it kind of still has rows and columns. You could have it stored on a hard drive, could be a cluster of machines, could be DNA. I told you some people managed, but do you notice something here? The upper part never changes. It's always the same. This is the beauty of data independence. You can swap the way you implement it. The look and feel to the user is the same. It's a table with rows and columns, period. This is the beauty of data independence. Then I told you about variety and data shapes, the 5 fundamental data shapes: tables, trees, cubes, graphs, and unstructured. By the way, somebody asked, it's a very good question. I tend to put images and videos and audio also together with the text, right? This is all the things that go into the ChatGPT box with what you can do with generative AI. This might evolve, right? Because the way you, so for example, behind the text, you might have who heard the word embedding? Maybe not a lot of you if you're not computer scientists. So there is a technology behind the text that uses linear algebra and vectors to represent the data. You could almost consider that it's a shape of its own, right? So maybe 1 year I'll update it with a 6th shape, I'm not sure yet. But for now, I put images, videos, text, all of in the unstructured box. But anyway, parentheses closed. The one thing we're interested in today is tables, right? So I'm going to focus on tables. The one thing that is the same across all shapes is that we need to store it somewhere as zeros and ones on some hard drive eventually. We need to compute, so it needs to go through some processors, CPUs, and so on. There needs to be a model. I'm going to come back to that. Essentially says there's rows and columns. There needs to be a language, that's SQL, that we are going to learn to process it. That might change with a different shape, but for tables, at least this is what we have. So now what is a model? So that 3rd level. The model tells you what the data looks like a table, and what you can do with it, project, select, and so on. I'm going to come back on that. It's a little bit like when you cook, you have a model that says, what do you use for cooking? The slide comes back. It's the ingredients, like salt, sugar, eggs, and so on, something that can be hidden. And what you can do with it, you can mix, pour, break, dry, bake, grill, melt, mince, mix, and so on, right? So in essence, it's just an analogy with cooking. This is the idea, right? Except that here we are talking about data. So what it looks like is going to be a table with rows and columns, and what you can do with it is going to have different verbs than this. But this is the idea. Now the magic with these 4 levels, storage, compute, model, language, is that the data independence limit is in the middle. This here is the data independence level here, right? Everything above it, model language, is the same. And what we swap, and we will do it during this lecture, is the levels here. We can, in the information systems for engineers, we had a single computer, that was your laptop. In this lecture, we are going to swap that with a gigantic data center with thousands of machines. What's incredible is that what's up there doesn't change. So this is why what I'm teaching to you today will not only be true for one laptop, it's also true for a data center. So I'm going to focus on that part. Now here are the takeaway concepts. Again, very high level, you will see it's extraordinarily intuitive. So for the model, we need to describe what we see. What do you see here? It's a table, right? Looks like also what you can open in some spreadsheet software like the Clay tablets. There might be other words. Some people might call it collection, relation, relational table, and so on, right? You might see a table as a collection of rows, for example. So these are all synonyms, but I put in bold the one that I'm going to be using, right? Table, collection, relation, relational table. It looks like this. Now, if you look closer, you have rows or lines or records or tuples or entities or items. The business people, they call it business object. That I love, right? So when they are talking to customers, business object, they actually mean one line of your relational table, right? Or a row, right? So these are all synonyms. This is one record. For example, if you have a list of people, let's say the list of all students who are registered in that course, every business object is one student, right? Okay. And again, these are all synonyms. Record, tuple, document, these are all the same thing. It's just a name for that. You could also look at the columns, right? So here too, we can call this an attribute, a column, a field, a property, a key, and so on and so on. This is, for example, the first name of each student, the last name of each student, the Leggy number of each student, and so on. The AHV number, the social security number, these are all attributes. So you see, we have rows, we have columns. Then some of the columns might actually be special because they identify somebody. For example, the Leggy number at ETH identifies you. So the Leggy number column is actually special, right? If I have it, I know what student it is. This is how we deal with bonus points at the exam, right? We do a join where we use the Leggy number in order to match the bonus points with the exam grades, right? It's very common to see something ID. So PID would be person ID, then you can have CID for course ID and so on, but this is just what we call a primary key because it identifies somebody. The social security number is also one way to identify somebody, the AHV number, right? AVS in French. So it's not true for every column. For example, the first name doesn't identify somebody. If I tell you Peter, then you don't know who this is, right? The first name is not enough, but the Leggy number is actually enough. You can also see synonyms like row ID, name, key might also be used in that context. So again, be careful. In some cases, like JSON, a key might be any attribute. In some other cases, the key might specifically designate a primary key that identifies somebody. All right, so we have rows, columns, special columns that actually identify the business object. And then we have the values. This is a single cell, one cell of your spreadsheet, right? So you can also, some people call it a scalar, maybe because they have vector spaces in mind where there's the vectors and the scalars, real numbers, complex numbers. But you could call it a scalar if you want, or an atom, or a cell, or a characteristic, or a fact. It's just what you have in a single cell, like this. You can also view that as the intersection of a column and a row. That gives you a single value. Who is following? Okay, that should be simple enough, right? It's a high-level view that I'm giving to you. It sounds trivial, but do not underestimate how important it is that a model is simple if you want to actually deal with it. That's why we have data independence. Okay, so that's the first part of my model, what the data looks like, the ingredients for cooking. Now, the second part is the verbs. What do you do to transform or modify or query that data? There is a very fancy name for that. I love it. I mean, I love mathematics. So the relational algebra. So just like you have algebra, with vector spaces and scalar products and so on, like the beautiful mathematics, you can actually treat tables just like mathematical objects, and you can define a whole algebra on that. I don't mean, so if there's mathematicians, just warning you, algebra has a very specific meaning. I think if I correctly remember, it's a vector space that is endowed with an additional multiplication-like operation. Here it's meant in a more generic way that we say this. But let me show you. So if we want to make it a bit more mathematical, one way to look at a table is to see it as a mathematical relation. It's something that establishes a relation between the attributes. There's a relation between your Leggy number, your first name, your last name, your date of birth, and so on. Mathematically, what is a relation is just a set of tuples. Not all of them, some of the tuples, and you can list them explicitly, right? For example, you can have a relation between a university and a city. What tuples are going to be in there? ETH Zurich, Zurich, EPFL, Lausanne, Unigenf, Geneva, and so on and so on. You can list them one by one. Each tuple in your relation is a row in your table. So if you know what a mathematical relation is for you, if you don't, forget that slide immediately and don't be bothered by the complexity. I'm just saying mathematically you can view a relational table as a relation in this way. Now, I prefer to look at this in this other way because it's more intuitive and that's also much easier to go into big data from there. So it's to define a relational table. First, what you see is a set of attributes. It's the headers, if you want, of your spreadsheet. So Leggy number, first name, last name, date of birth, and so on and so on. So that's called what we call the schema. Typically, it's what columns you're going to have. And then the rest of the table is basically going to be, let me say a list of tuples, a list of business objects, right? A list of persons in that case, right? Every row corresponds to a person. So if you ask me, what is that table? It's just a list of tuples. How many? 6. There are 6 tuples, 6 persons, right? Why did I say set, bag, list? Well, it depends if the order matters to you. Do you have a specific order in the people? And if you allow duplicates or not. Are you fine if you have twice the same row in the table? If the order matters, then you need a list of tuples. If the order doesn't matter and you don't want duplicates, then you have a set of tuples and you don't care about the order and you don't have duplicates. A bag is if you don't care about the order, but you still allow for duplicates. All right, so this is why you can have a set, a bag, or a list of tuples, and that's the extension. This is a table, mathematically. Who is following? Okay, great. Formally, a tuple for the computer scientists is what you could also call a map. Mathematicians might not call it a map, they would call it a partial function from strings to values, like this. I'm taking here the second tuple, to Ramanujan, Srinivasa, India, right? I can also view that second tuple like this. Now I'm using the function symbols from mathematics. This is a partial function that maps some strings, 4 of them, not all of them, just 4 of them, PID, last first country. I'm mapping some of the strings to values. PID is mapped to 2, last is mapped to Ramanujan, first is mapped to Srinivasa, and country is mapped to India. So this is a partial function. Partial function, why? Because it's not associating a value to every possible string, but only to these 4, right? So again, this corresponds to this mapped to this mapped to this mapped to this, and this mapped to this. It's just the same thing. So this is how you can see that a row in my table can be seen as a mathematical partial function. And again, computer scientists call that a map because it's mapping the attributes on the left to values on the right. So every row here has its own partial function that looks like this. Okay? Who would be able to, if I give you this one, to give me the other 5 very easily? Who would be able to do that? Right? Exactly the same slide, just replace the values with those of another rows, right? It's that simple. Now, computer scientists, when they want to store that in a text file, they have another way of doing that, and that's actually something we'll cover in that lecture, that looks more like this. It's technically the same thing, it's just something that we do in computer science. Who knows what syntax that is? Yes, tell me. JSON, exactly, and that will be covered in that lecture. So this is JSON. This is how we store as text in a text form some one of the rows in the that is in our tables, still the second one. Okay. But again, for the purpose of tables, you don't actually do this. That we'll do later in the semester. You actually do this. This is the way that the database people look at one of these, a record, right? It has the headers, the name of the attributes, and then it has the values in there. In my case, just for a single record, and then you assemble many records into a table. The order of the attribute is totally irrelevant. Just like in a mathematical function, there is no particular order in which you map the input to the output. Now, what do we do if you have several records? Let me take 3 records that are just these partial functions. I have 4 of them. Do you notice something? They actually map exactly the same attributes in there. So what can you do? You can merge them like this, right? This is technically how you obtain a table. It's merging all of these records because they have exactly the same attributes. You merge them into a single table. If you cannot do this, then it's not a table. That's an example where it's broken. In that case, I have these 3 records, but you can see they don't all have the same attributes. The first one has name, first name, physicist year. The second one only has first name, physicist year. And the third one has a country, a name, a first name. It doesn't have a physicist value and year. That here is not a table. It's still a list of records, a list of partial functions, but they don't have the same attributes, so you cannot paste it into a nice table. Here we say that the relational integrity is broken, right? So here it's working, it's a table, it's all the same attributes. Here it's broken. What else can we break in a table so that it's no longer a table? So this is a table, this is not a table. So what is happening here? That it's no longer a table. Well, we have a table in a table. Do you see the blue things here? Here, here, and here. I have a table in a table. That is breaking another rule of tables that you cannot have a table in a table. You can only have atoms like atomic values, right? Strings, numbers, dates, and so on. You cannot have a table in a table. It's like the Inception movie, right? A dream in a dream in a dream in a dream. You can have a table in a table in a table in a table. Well, you cannot have that in the relational model. You cannot have a table in a table. That's called atomic integrity. So this is forbidden, and this is allowed, right? And there is a third rule that you can break for a table no longer to be a table, relational table. It's called domain integrity. Do you notice how in the same column, the values look the same? In the first column, it's all names. These are strings. The second column, it's first name. These are strings. The third column are Booleans, true and false. And the year is an integer, 1905, 1936, 1842. This is called domain integrity, where within a column, you always have the same kinds of values, which are called types. Here it's broken. Why is it broken? Well, you can see in the physicist column, there are Booleans and there are integers. So this is broken. It doesn't have domain integrity. The same goes into the last column. It's broken because 2 of them are integers and the third one is text. Of course, as a human, you can recognize that you can convert it to an integer, but the computer cannot do that, right? So you would need to clean it up if you want. You might clean up the -1 to true, and you can clean up the 42 to 1942 if you want. Then you have domain integrity. So we have these 3 rules: relational integrity, atomic integrity, and domain integrity that all relational tables have to respect. If you fulfill these 3 rules, then you have a relational table. For whom is that clear? All right. So the intersection of that is SQL. This is what we are discussing right now. What happens if you break the rules? Well, you enter the fabulous world of NoSQL. In fact, we are going to be breaking these rules throughout the semester, but not today. Today, I'm going to stick to the 3 rules fulfilled, and we'll break the rules in the rest of the semester. Okay. So we have a relational table defined in this way, and now we can manipulate it with an algebra. So what can we do? So for example, in mathematics, you have addition, multiplication, scalar product, inner product, outer product, and so on, right? So when you have tables, instead, what you can do is union, intersection, subtraction, selection, projection, rename an attribute, a relation, grouping, sorting, Cartesian product, joins, and so on, and so on. You have an entire toolbox of things that you can do with relational tables. So I'm going to show you a few of them, and you will see it's very intuitive. This is one thing you can do to a relational table. You can select some of the rows. For example, you can select everybody who is in the UK, right? So it's Alan Turing and Ada Lovelace, and you select them. By the way, this is something you can do in a spreadsheet software, right? You can select a table, then you can click, I think, on filter data, and then you click on a header, and then you select the values you want, and it's going to filter only specific rows, specific records. Who already did that? Some of you, right? Well, this is one thing you can do to relational table. You're basically taking a subset of the records and filtering specifically, in that case, the people who are in Great Britain. That is called selection. Now that's on the rows. What if we do it on the columns? Well, it has another name. If you do it on the columns, this is called projection. By the way, you can also do it in a spreadsheet software. All you need to do is click on the columns that you want to get rid of and click on hide in the menu. Hide, hide, hide. So if you hide PID and hide country, you end up with last and first. This is called projection, right? It's very visual, very intuitive to understand. Then there is grouping. Grouping means that you notice that the values on the left, they repeat. You have foo, 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 then you have bar, 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 and you have foo bar and foo bar. Then you can group all the foos, all the bars, all the foo bars, and sum over the values. An example of that is, imagine I give you a list of all cities in Switzerland, all towns, Gemeinde, together with the number of inhabitants and the canton that it is in. Then I can group by canton and sum over the inhabitants of the Gemeinde in each canton. That is a group by. Then I end up with a list of 26 cantons together with the total population in every canton. So foo bar and foo bar here would be the cantons, and A would be the inhabitants. Okay? This is called grouping. Aggregation is another way you can call it. Another thing you can do is called sorting, but here it assumes you have a list of records, that the order is actually important. You can sort by first name, sort by birth date, and so on. Again, this is something you do very easily in spreadsheet. Again, you select the table, filter data, you click on the header, and then you click on ascending or descending, and it reorders your rows. So very intuitive. Then here is a bit fancier, a bit less. You can do it also in spreadsheet software. It's just a bit more complicated. It's called the Cartesian product. What happens here is we're going to make all possible combination of a record coming from R and of a record coming from S. So there's 2 rows in R and 3 rows in S. Gives me 2 times 3 combinations, 6 possible combinations. That's called the Cartesian product, right? You try to match every row on R with every row on S and get all possibilities listed. Then we have the join. It's very close to this, except that you filter. What is the difference? Is that in a join, you don't match any row with any row. You only match the rows if they actually match on some value. What I mean is that this row right here has b equals 1. So we are only going to match it with this row here because it also has b equals 1. We do not match it with this one and this one because they have a different value. Here we do. Here we match 1 with 1, 2, 3. But if it's a join, we really pay attention to these values being the same. I get this, then 2 is matched with 2. I get that. And 3 here is not matched with anything. So that's why it's not there. For whom is that here? That's called the join. It's extremely powerful. Join is when you have several data sets and you're putting it together to learn even more information. Extremely powerful. Now, the next thing I want to tell you is that when you decide on the data that you want to store, you typically have to design your schema. You need to decide what columns you're going to have, how many tables you're going to have, and what columns they have. Now, if you get it wrong, bad things are going to happen. They are called anomalies. Delete anomalies, update anomalies, insert anomalies. I'm not going into the details of that, but basically, if you're not careful about the way you design your schemas, then you're going to end up with duplicates, you're going to end up with discrepancies, like you update here and you forget to update there, and then you have disagreements between the same data at 2 different places. These are called anomalies. And there is a whole theory that we studied in information system for engineers on how to avoid the anomalies. And this is called normal forms. So the idea is that there is a concept called functional dependency that tells you that some value, some column might depend on another column. An example of that is the name of a lecture at ETH depends on the ID of the lecture. Every lecture at ETH, every course at ETH has a code that looks like that. You probably see it in my studies. If I give you the lecture ID, then you can tell me the name of the lecture. That's called the functional dependency, right? Based on that, I can have functional dependencies that if I know the value of some columns, like if I know the Leggy number, the name, the lecture ID, then I can infer the name of the other columns. That's called a super key when it's enough to identify everything. Then you can try to remove some of the columns and you can still identify everybody in here. And if you manage to take a minimum of that, now you can not remove anything anymore. That's called the candidate key. And one of them, there can be several of them, and one of them is going to be a primary key. An example of that is what I said before, the social security number of a person, the Leggy number of a person, and so on. So the idea is that then when you have all of these fancy mathematical stuff that you define on tables, you are basically able to define what is called a normal form. A normal form is a constraint on a table that it must fulfill if you don't want to run into problems. The first normal form, it's easy because I've already told you about it. It's when you cannot have a table in a table in a table. That's what we also called atomic consistency. It turns out that another name for that is first normal form, but it's really the same thing as what I told you before. You cannot have a table in a table in a table. That's called the first normal form. And in information system for engineers, we also, so this is a counterexample. This is an example. In information system for engineers, we study another normal form called the Boyce code normal form that basically says that it's not allowed to have dependencies from something that's not a super key. Computer scientists also know other normal forms. There's the second normal form, there's the third normal form, there's the fourth, the fifth, the sixth normal form, and probably many others. And you're supposed to respect that. In a relational database system, you're supposed to actually obey all of these rules. Who understood what I told you about normal forms? Who did not? Who is lost with the normal forms? Please raise your hand. I want to see more hands. Who is lost with the normal forms? Yes? Yes, exactly. So, it's just a choice of how much you want to achieve. So basically, the sixth normal form is extremely strict. The second or third are a bit less strict. It's like security levels, if you want. You can choose your security level. So basically, yes, if you are in the first normal form, but not in the second one, then you break the rules of the second normal form. That's the idea. Maybe there's even more than six. I mean, people keep inventing them. At some point, it's a compromise. Most people are going to be in the third normal form. Most databases target the third one, and they don't try to be in the fourth or fifth or sixth. I think the third one is a quite reasonable compromise. In the end, it's a compromise, right? If you go high, like 5, 6 normal form, it becomes difficult to implement. It's a compromise between how easy it is to actually do and how much guarantee it gives you, right? The idea of the normal forms is that you use them in a database where you modify the data all the time. You have an online shop, people place orders, you ship items, the inventory keeps changing, then you need the normal forms. Otherwise, you're going to go crazy because you're going to have duplicates in your data, inconsistencies, and so on. This is what the normal forms are for, right? Yeah, thank you. So now everybody raise your hand if you're lost with normal forms. You're not lost? Okay, I see some hands moving like that because I have great news for you. I have great news for you is that we are going to throw away the normal forms in that lecture. All of that just in order to throw them away. Well, there's a reason, in fact. It's that the normal forms, they are really, again, this online shop thing. You have a database system and you have customers. Your website is alive, right? There are people placing orders. You need the normal forms because you're updating your database all the time. But in the case of big data, we don't care about modifying the data. What happens when you have a data? You download it and then you query it. This is pretty much what happens. But your data doesn't change. It's just the file you downloaded from the internet, right? And then you're analyzing it. For this reason, in this lecture, Big Data for Engineers, we are going to throw away the normal forms. We don't care about them anymore. They're gone. We might even throw away the first normal form, by the way. We'll see tables, inner tables, inner tables in that lecture. And that's not going to be a problem at all, right? So this is what's going to happen. And this is basically why I didn't take the time to go into the details of normal forms, and you actually don't really need to understand. I'll tell you whatever you need to understand. But again, the reason is we're throwing them away, right? But technically, when you throw them away, you first need to know that they exist in order to throw them away. It's something that you need to be aware of that you're actually doing. Okay. So we're throwing away the normal forms. That's one less thing that you need to worry about. But for those of you who didn't take information systems for engineers, the one thing you can remember, because that's easy, is the first normal form says you don't have a table in a table in a table. Getting rid of the first normal form means that you accept to have a table in a table in a table. Okay. Who feels better now that I've told you we're throwing away the normal forms? Okay, very good. All right, now I'm going to SQL. SQL, you're going to have an exercise next week, so you're going to have the opportunity to practice it, to understand the construct. You will see it's relatively easy to learn. So I'm going to just drop a little bit of this at you. First, it's part of a whole language landscape. There's the languages for programming, like you might know Java, C, Python, and so on. That's the first category of languages. Then you have the query languages on the right that are functional. Typically, you have SQL and so on and so on. We're going to go into them. Then you would have the machine learning section. That's not part of this lecture, but you also have languages for machine learning, right? You can do it on the low level, on the high level. What we are going to be looking at this lecture is the right part with databases, both the low-level languages like Spark, MapReduce, and so on, and some higher-level languages, including SQL. Now, SQL was invented shortly after Edgar Code actually invented the data independence. So we have Don Chamberlain and Raymond Boyce. Boyce is the same as in the Boyce Code normal form, by the way. He gave his name to the normal form. And all of that happened in San Jose, in California, in the US. Actually, the place still exists. I don't know if it's still called the same, but it's there's still an IBM laboratory in San Jose. And so in the 70s, there was this first commercially available relational database software that basically implemented the ideas of Edgar Code. They got their first customer in 1977. And now I don't think there's a single company in the world that doesn't have a relational database. Like everybody has a relational database now. You might know Oracle. There's also IBM, Microsoft. These are the big three. And then there's many open source databases like OpenSQL, not OpenSQL, PostgreSQL, MySQL, and so on. Right? Now, all these databases, relational database systems, they implement a language called SQL. It used to be called SQL like this, S-E-Q-U-E-L, Structured English Query Language. The goal was to be easy, but they ended up with a trademark issue because somebody wasn't happy that it was called SQL like this, so they renamed it as SQL. But you still have people from the older generation who still say SQL out of habit. You can say either SQL, SQL, just know that it's the same. Basically, if you hear me say SQL, because I interacted with some of these people, so I kind of got into this habit, just don't be surprised. SQL, SQL, that's the same thing. Okay, so the idea of SQL is that it's declarative. Declarative means you go to the Mensa and ask for the veggie menu. Imperative would be you go home and you cook. That's the difference. In Python or in C or in R, you need to cook yourself. In SQL, you just go there and ask for the veggie menu. That's called the declarative language. And the nice thing about the declarative language is that you don't care how it's implemented. And we'll see that we can swap here to a data center and the language still remains the same because it's declarative. And then it's functional. We'll come back in a few weeks to exactly the details of that. It's the idea of expressions that nest. Just like you have a table in a table in a table, you can have an expression in an expression in an expression. Now you might not know it, but you've been doing that since primary school. When you have a multiplication inside an addition, inside a multiplication with parentheses, you've done that in primary school. It's exactly the same idea, except that you might have something else than addition and multiplication. Okay, so let me show you some SQL. And again, you're going to have next week as exercises to go through that. In order to select specific rows, all you need to write is select star, means all columns, from persons, that's the name of the table, where, and your criterion. Last name must be equal to Crusher. And you see that the only row in the original table over there that matches this criterion here is this one here in the middle. You see, last name, Crusher. So what this does is that it only selects this one and outputs this. For whom is that clear? That's a selection, that's SQL. How do I project? Well, instead of the star, you just write the columns you want. I only want first name and birth date, for example. So this one and this one. So I replace the star with their names and I get that table. You can also rename using as, first name as who and birth date as when. You just rename the columns in here. You can order, just say select from order by birth date, and now you have it in the right order. You can do it ascending, descending, just like in spreadsheet. You can say ascending, descending as well, right? You can also group, for example, how many per century. So you say group by century, and then here you count. For every century, you see 23, there's 2 of them. 24, there's 2 of them with the count, and now you have 2 and you have 2. That's a group by. You're going to have plenty of exercises to practice that. After the group by, you can also further filter. For example, you might group and you only keep those that have more than a certain count. Here, I change the data. I have 3 times 24th century and 1 23rd. I'm only keeping the groups where the count is more than 2. That only keeps that group 24. The one thing you need to learn by heart is basically this. There is a specific order in the clauses. It's always, always, always select from where, group by, having, order by, limit, offset. Limit offset is just to paginate. You basically only want the first 10, the next 10, the next 10, the next 10, just like the Google results. So that's what limit and offset do. Learn that by heart. Select from where, group by, having, order by, limit, offset. That's already 80% of the way through knowing SQL, right? And you're going to have plenty of exercises next week to get you used to doing that. So again, for many of you, you already know that. For the others, you will be surprised how easy it is to actually learn, and you do it interactively. You have a Jupyter notebook, type your query, and you see the results. It's much smaller than in a spreadsheet. It's much faster than in a spreadsheet. In a spreadsheet, you need to click at a lot of places. But with a language like that, you just type what you want, and you immediately see the results of the query, right? Who feels comfortable with that, has an intuition for what that does? All right. So in that case, we are considering all the Gemeinden, the cities in Switzerland. You have a list of everybody in Switzerland. We are grouping by the city they live in. We only keep the cities with less than 100,000 inhabitants, ordering by population descending, the larger first, the smaller then. We are skipping the first 20, sorry, offset 20. We're skipping the first 20 and outputting the next 10, right? So I don't know what you will end up with, maybe Interlaken, I don't know, yeah. Okay, again, there's nothing that beats practical experience. So I really recommend solve the exercises that the TAs will prepare for you next week, and you will completely master SQL and be able to write the queries. Okay. I think I have a few more slides, but it's already 10. So I'm going to stop here. I will finish the few more slides that I have, and next week we are going to have our first real lecture with actual material specific to big data. We are going to see how we can store enormous quantities of data in the clouds as a cloud service, right? So cloud storage. So thank you very much for attending today's lecture. This week, there are no exercises. All we ask you is to test the Docker Compose setup that the TAs will show to you. If you have issues, go to the TAs, they will help you. The first exercise sessions will be next week, right? But you can already register to the groups. For the continuing education students, this year we put a special flag on one of them on Fridays to say this is continuing education friendly, in the sense that you can converge to the same one and work together, right? Okay, so thank you very much, everybody. Enjoy the semester and see you next week at 8 a.m. Thank you.